Dr. Thompson here again from Taylor University, and this time we're going to do an integral using an idea called trigonometric substitution. This is a little tricky, but it allows us to move a problem that has square roots or some other reason that it's difficult to do to a setting that's trigonometric, whether it's sines or cosines or tangents and secants. Those trig identities that we don't really seem to care for are actually really useful, so we're going to use several in this problem to get this one done. So here you see I have the square root across a difference across 4 minus x squared, and you cannot separate a root across that. You can do roots across products and quotients, but not sums and differences. So this is not 2 minus x if I try to separate that square root. Instead, let's think about trig identities we know, like this one. Cosine squared theta equals 1 minus sine squared theta. That means here you have a difference of 2 squares, because that's really a 1 squared, and I can convert it to something I could square root. So I would like for x to be basically a sine theta. Of course, I also have this 4, right? That 4 is a 2 squared. So we're going to make this substitution. We're going to make the substitution x equals 2 sine theta. And the 2 is because that's the square root of 4. And so you'll see that this will work out quite nicely in a minute. This is a substitution like a W substitution, but it works a little differently because x is on the left side, not the right. So when I take the derivative of the substitution so that I can change my differential here, I'm going to get dx equals 2 cosine theta d theta. So I've already solved for dx, and I'm going to multiply by this differential, not divide, by the extra stuff here. So that's going to change the main part of the integrand, but we also have to change the limits, and this is backwards as well because x is on the left. So let's go ahead and change our limits. When x is 0, which is the bottom limit here, this is x, then we would have 0 equals 2 sine theta, or 0 equals sine theta. And you have to think about when that happens on the unit circle. So let's put the unit circle over here. Remember, sine is the y value of the unit circle. And you have a y value of 0 right when theta equals 0. And then the top is 2, which really means that sine theta equals 1. And that happens at the top of the unit circle, which is when theta is pi over 2. All right, so we're going to make those changes. We're going to change the limits of integration. We're going to change x here to 2 sine theta, and we're going to change the differential. So we're going to do quite a bit on the next slide. So let's go ahead and make all those changes. All right, so when you look at this slide, you see that we have changed everything. We have changed the limits to theta equals 0 and theta equals pi over 2. We've changed x to 2 sine theta, but remember that x was squared, so this becomes 2 times 2 is 4, and then the square of sine theta. Because remember, squares and square roots, you can go across products. And then our differential changed to 2 cosine theta d theta. Now, the point of this was to get rid of this root. That is the problem. You don't want to lose sight of what we're trying to do because there's a lot of steps involved in trig sub. But ultimately, we want to get rid of this root. So we purposely picked 2 sine theta so that we would have 4 twice. So within this root, I'm going to factor out the 4. So down here, this 2 I've brought to the outside of the integral, and within the root, I factor this 4, so that I have 4 times the quantity 1 minus sine squared theta, and then my cosine theta d theta. Roots do go across products, so let's root the 4 separately from the 1 minus sine squared theta. Let's do that on the next slide. So here the 4 has been rooted to a 2, then I've got square root of 1 minus sine squared theta along with everything else I had. The 2 and the 2 can come outside the integral as a 4, and remember our whole point in choosing to do a trig substitution was this identity, that 1 minus sine squared theta, which is what I have here in the root, equals cosine squared theta. So let's make that change, and that's not a substitution, that's just a trig identity. So finally, I'm at the point where I have a square root of one particular term, and when I square root the square, it should just become cosine theta. There is a subtlety I want you to think about, which is that normally if you square root x squared, that is not x, that is the absolute value of x. However, you have to remember our limits of integration are 0 to pi over 2, and within this first quadrant, from 0 to pi over 2, cosine is positive in that region. So it's okay just to write cosine theta in this case. And let's do that on the next slide. Alright, so you can see here on this slide I have changed the integrand just to cosine squared, and now I'm going to use another trig identity. You might have learned this by solving for cosine of 2 theta when you were in trigonometry or in precalculus, but we want to solve for cosine squared. Cosine squared is equal to 1/2 plus 1/2 cosine of 2 theta. And the reason why we want to do this is because I don't actually know the antiderivative of cosine squared, but I can do the antiderivative of a constant, and cosine of 2 theta I can do with a w substitution. So I'm going to change the entire integrand using that formula, that trig identity. And of course, these 1/2s I can bring outside and bring the 4 down to a 2 by multiplying those. So let's go ahead and simplify on the next slide. Okay, so you can see on this slide that I have now got a 2 on the outside instead of a 4, and I no longer have the 1/2s here. And this next part, you should get in the habit of doing in your head after you've done enough w substitutions, but I'll work it out this time. The 2 theta, I really would need to just be w or whatever variable I have. So I'm going to make w 2 theta, and then dw would be 2 d theta. So that means I'm going to double my limits of integration, so now it's 0 to pi. Then it's 1 plus cosine w, and dw, of course, is 2 times d theta, so d theta is dw over 2. And that 2 on the bottom I just canceled with the outside. Okay, and that's a bit backwards from the trigonometric substitution I made. Now, on the next slide, we'll go ahead and do this integral, and in this case, we know the antiderivatives of both terms, so we can finally do a basic integral. All right, now to finish out, we just need to do this antiderivative, and because we've changed our limits of integration each time, we're just going to get a number and we're done. We're not going to switch back either of our substitutions. So this will become w plus sine of w, evaluated at 0 and pi, and at pi and at 0, sine is 0, so it's really just going to be pi plus 0 minus 0 plus 0, which is just pi, and that is our final answer. Okay, so the next few slides are what this might look like on your homework, but it took me 3 slides because these are pretty involved. But you should write out all the steps I've been showing you here, because the most common mistake I see with trig substitution is that even students who understand it, they go too fast, they try to skip steps, and something goes horribly awry. So here you can see I started with the original integrand, and then I made the substitution. I changed x, I changed the limits of integration, which perhaps I should also write that as well. We should maybe make it short here. So when x was 0, theta was 0, and when x was 2, theta was pi over 2. You don't need to do that, but there's no real harm in doing it. And then my differential became 2 cosine theta d theta. I factored the 4, and then it became a 2. And so I also have the 2 from my differential. At this point, I have the 4, I have the square root now of cosine squared using the identity, and then I have cosine theta here. That altogether becomes cosine squared, and I have to use another identity right away to change that to 1/2 plus 1/2 cosine of 2 theta. Next slide, I took the 1/2s out and multiplied them by the 4 to get a 2, and this is what I was talking about doing this w substitution in your head. If cosine of 2 theta, that would become sine of 2 theta times 1/2. That's the w substitution on just that part. If you kind of just memorize that, it'll save you a little bit of time. And then 1 became theta, and when you plug in pi over 2, you still have this 2 here, so that'll be sine of pi, which is 0. Sine of 0 is also 0. So you're going to get 2 times pi over 2, which is pi. So that'll give you the same answer. All right, so that is a basic example of trigonometric substitution.